Hey there, Mr. Sutton here with the IM3 Honors 1-5 Extra Practice Number 2 solutions on function families and even versus odd functions. In this one, we are trying to solve a puzzle. Let's take a look at that. So here is the puzzle we're trying to solve. We want to know, what did the king of the real valued functions say to the imaginary numbers? And the idea for this one is we are given a bunch of functions in both algebraic and graphical form, and we need to match those with the domain and ranges listed down here below. And there's a few of them. Whenever we figure out what letter we should have as a match, we just put that letter above the problem number in these blanks down below. And this will all spell something out when we're done. So let's go ahead and see what the king has to say. For the first problem, we have f of x equals 2x plus 2. We want to know the domain and range for all of these. For this one, since this is just a line, that means that the domain, the x values that you're allowed to plug in, the places it covers horizontally, is all the x values, all real values. And it means that we can also hit all the y values as well, since this is a slanted line rather than a horizontal one. So all reals for the range as well. So we're looking for all reals for both of these. That's going to be choice M. That's what this X and this symbol here means in the set of, this little weird E symbol. And then this weird looking R in cursive, I guess, or whatever, this is the kind of the shorthand for the real domain of numbers, domain of real numbers. So M is what we need. Let's find choice 1. That's right here, or box number 1. So we'll put an M right there. And you do need to be a little bit careful on this. There are a couple duplicates. For example, 9 gets repeated along with, I believe, 19 as well, maybe some other ones. So just be on the lookout for using a letter more than once every now and then. For number 2, they're giving us x squared minus 1. This is a quadratic. So the domain of a quadratic function is all the real numbers. You can plug in all the x's you want. Nothing bad happens. Now the range, however, is a little bit limited. Since this is a parabola, when you graph it, it turns around. So let's figure out which way this thing's going. Since we have a positive x squared, that means this thing is opening up. So we're going to have y greater than or equal to whatever the minimum value is for this. Now for the minimum value, well, the lowest that this thing can be is if you plug in 0 for x. Because if you plug in anything other than 0, this is going to get squared, become positive. The lowest number you can get is if you plug 0 in here and get 0 back. So y is going to be greater than or equal to 0 minus 1. And then if you just subtract 1 from 0, we see that y is actually greater than or equal to negative 1. That's the minimum y value that we can achieve with this graph no matter what x values we plug in. So taking a look for all reals and greater than or equal to negative 1, that's this choice N right here, all reals, and y such that y is greater than or equal to negative 1. So N is going in spot number 2 right there. Number 3, f of x equals 1. This is a constant function, which is graphed as a horizontal line going through 1 in this case. So because of that, the domain is still all real numbers since it is kind of linear. However, the range, we can't hit all the y values. There's actually only one y value you can ever hit with this thing, and that's the y value 1. It's always 1 no matter what you plug in. So we got y equals 1 exactly for the range. So we're looking for all reals and y equals 1. And that is right here, choice B. So let's put that in spot 3. For number 4, we've got our square root function. Now for the square root, in terms of x values, we don't want to take the square root of a negative. So we only want to have square roots of 0 and positive numbers. So we're going to set a condition that x is greater than or equal to 0. Now in terms of the range, the output for this thing, since the lowest number you can plug in here is 0, the square root of that would give you 0. You can't get a negative number out of this square root. So that means that the range is also going to be greater than or equal to 0, but y instead of x. So we've got both of these greater than or equal to 0. Checking out my answer choices, Let's see here. Where is that? Right here in the beginning, choice A. So A is 4. 4 is A. For number 5, we have f of x equals 1 over x. That's the parent function for the rational functions. For the domain, we don't want any x's that make this thing undefined. So x, in this case, the only thing x can't be is 0, because we would be dividing by 0 in that case. So x not equal to 0 is the domain. For the range, the only y value this thing can't hit is also 0. Now, the reason behind this is to get 0 with a fraction, you would need to have 0 in the numerator. Since our numerator is a constant other than 0, it's impossible to get 0 no matter what you plug in for x. So we're looking for not 0 for both of these. Not 0 for both is going to be choice I. So 5 right here is I. For number 6, we have absolute value of x minus 1. This one's going to behave kind of similar to the quadratic function, even though it is an absolute value function. So for the domain, absolute value can handle anything, all real numbers. Nothing worries us about that. Now for the range, though, absolute value is kind of limited. The lowest that this absolute value of x can give you back, since it always gives you back 0 or positive numbers, the lowest this expression can be is 0. So we're going to have y greater than or equal to whatever 0 minus 1 is. That's the minimum value. And that's just going to be greater than or equal to negative 1. So we have all reals and negative 1 greater than or equal to. Where's that? Looks like right here. And we've actually used this one before, but we're using it again, this time in spot 6, which is right there. For 7, we've got another absolute value function. Just like before, the domain is going to be all reals. It doesn't matter what you plug in here. Absolute value can handle it. Now for the range, since the whole function is inside an absolute value sort of deal, that means that the output of the entire function can be, at minimum 0 or positive. So greater than or equal to 0 for this one. And that is going to be O right there. So that's going to go in spot 7. For number 8, we have the fourth root of x. This is an even radical, so it's going to take a lot of its behavior from the square root function that we saw earlier. For example, we don't want to be taking an even root of a negative number, so x has to be greater than or equal to 0. We also can't return anything less than 0 because of that restriction on the domain. So that means that y is also going to be greater than or equal to 0. So greater than or equal to 0 for both, that's A, just like it was for the square root function. So we're putting that in box 8. For number 9, we've got a modified square root function going on, square root of 1 minus x. So our domain restriction, the stuff inside here has to be greater than or equal to 0. We don't want to take the square root of a negative. So I'm going to start by writing 1 minus x greater than or equal to 0, and then I'm going to solve for x in this situation. Now to solve for x, I can quickly just add x to the other side, and I would have 1 greater than or equal to x. But I don't want to write it like that, so I'm just going to flip everything around and write x less than or equal to 1. And if you think about it now, if I plug in 1, this thing comes out 0. If I plug in things less than 1, that either gives me something between 0 and 1, or it gives me negative numbers if I go negative enough here. Like if I plug in negative 5, this becomes 6 inside, which is fine. Now in terms of the range, obviously we can't get anything less than 0 out of the square root. Is there an upper limit on what we can get? Well, I can get as high as I want for outputs on this if I plug in a negative enough number, since this negative would give us a positive. So I'm going to say for my range, y greater than or equal to 0, I'm confident I can reach any y value I want above 0. So we need x less than or equal to 1 and greater than or equal to 0 for y. Let's see if I can find that. It looks like that's E right here. So that's going to go in spot 9, which is right here. And also there's another 9 over here that we don't want to forget about. For number 10, we've got another quadratic. So just like before, the domain on that is going to be all the real numbers. Now for the range, Since the whole function is just this one quadratic piece, the smallest that this can be is 0, and it can be as high as we want. So we're going to say greater than or equal to 0 for the y values. So all reals greater than or equal to 0, that is going to be O again. So that's going in spot number 10 right down here. For number 11, this is our first encounter with a cubic function, albeit a negative one. So the domain on cubic functions, you can plug in anything you want. Same thing with the range. You can get any y value you want, since this thing, whatever it does in between the end behaviors, it goes up and down forever in either direction. So the range is going to be all reals. So all reals for both, that's going to be m going in spot 11, which is right there. For 12, we have an exponential function. So because we have an exponential, the domain is going to be all real numbers. I can plug in anything I want for x as an exponent, and we'll be able to do something with it. Now for the range, we're a little bit limited. I can't get 0 if I start with something that's not 0 and raise it to a power. I also can't get negative numbers if I start with something positive and raise it to a power. So this is going to be greater than 0, strictly greater than 0 for the y values. You might also know what the graph of this thing looks like. We have a horizontal asymptote as we move to the left at y equals 0. So can't have 0 or anything lower. Let me look for reals and greater than 0. Reals and greater than 0, that's going to be s, so that goes for spot 12. For 13, we've got another rational function. Just like before, we want to make sure that denominator, x plus 4 in this case, does not equal 0. So that means that if you subtract 4 here, x itself should not equal negative 4, because that would zero this out here. Now for the range, because I have something that's not 0 in the numerator, that means I cannot get a y value of 0 out of this. I should be able to get everything else, but y will not equal 0 for the range. So we got not equals 4, negative 4 rather, not equals 0, and that should be easy enough to spot. Negative 4 is kind of random. That's right here. That's going to be h. So that's going in spot 13, which is right there. For number 14, on the face of it, this looks like a square root function, and it kind of does have some of that behavior, but it is actually more specifically a semicircle if you were to graph it out. Now, if you didn't know that, that's okay. We're still going to analyze it using our regular tools here. So with square root functions, like always, we want to make sure that the stuff inside the radical, the radicand, if you will, is at least 0, so greater than or equal to 0. Solving this equation is a little bit tricky though. So we're just going to kind of reason this out. So if I need this thing to be greater than or equal to 0, so positive or 0, well, if I plug in 0 itself, 4 minus 0 is 0, so that's fine. As I start moving further away from 0 for x though, I plug in 1, I'm still good. 4 minus 1 squared is a positive. How about 2? 4 minus 2 squared is 0, so that's still okay. Now how about 3? 4 minus 3 squared, that would give me a negative number, so we're outside of that range of values that we want to be in. So 2 is the biggest number that I can plug in and still get something that's at least 0. How about going the other direction? Well, negative 2 would also give me 0 if I plug it in for x squared. If I plug in negative 3, that would give me 4 minus positive 9, because negatives become positive when you square them. So that would break this condition going the other direction. So I don't want to go further to the left than negative 2 and further to the right than positive 2. Therefore, at the end of all this reasoning, I'm saying that we want our x values to be greater than or equal to negative 2 and less than or equal to positive 2, between negative and positive 2, including those values. So that's the domain. The range is also a little bit tricky. So for this one, let's start with kind of the minimum value. So we can't have something that's less than 0 coming out of this function. So I think we can confidently say x, or y rather, has to be greater than or equal to 0 for part of the range. Now there's another part of the range though, the upper limit on this thing. How high can we go? We're only allowed to plug in x values between negative and positive 2. If I plug those in, then that's going to give me 4 minus 4 essentially, so I would be taking the square root of 0. So that's kind of the minimum value. So the further away I get from these 2's here, the higher my value is going to be for the function. The furthest away I can get from negative and positive 2 is 0. If I plug 0 in here, so my maximum value, this thing's going to be less than or equal to 4 minus 0 squared. That's going to give me the square root of 4, which is just 2. So y is going to be less than or equal to 2. So I'm looking for a couple things. I'm looking for this negative 2 stuff with the x, and for the y, I'm looking for 0 less than or equal to y less than or equal to 2. So all of that on my shopping list, I'm seeing right here in choice R. Here's the negative 2 to 2, here's the 0 to 2. So we're putting an R then in spot 14, which is down here. For 15, we've got 2 times the sine of x. This is obviously a sinusoidal function. It's a wavy function. Now with these sinusoidal functions, like sine and cosine, the domain is going to be all reals. You can plug in whatever x's you want. These things go forever to the left and right. No issues there. For the range, the range of sine, normally it bounces back and forth between negative and positive 1 for the y values. If you stick a 2 out in front of it, you're doubling all the values it returns. So now the highest you can get is positive 2, and the lowest you can get is then negative 2. So negative to positive 2 is what we're looking for the range. So all reals and negative to positive 2. I see that down here with letter y. So that's going in spot 15, which is right here. So there's a whole word. This is our first word here, my. For number 16, we are seeing our first logarithmic function. This is the natural log. ln is just log base e. Now for the domain on these, we can't take the log of 0 or negative numbers. So this x has to be greater than 0. For the range, we can actually get any values we want. If you do ln of 1, you'll get 0 itself. ln of numbers less than 1 but greater than 0, has to be bigger than 0, will get you your negative numbers. And you can go as high as you want by just plugging in a high enough x value, high enough positive x value. So range is going to be all reals. So greater than 0 and all reals, that's going to be f right there. So that's going in spot 16 right there. So we have another word completed, from. For the next several problems, we have a graph that they're giving us, which on the face of it ought to help us out. But you also have to kind of recognize which function family you're dealing with, because a graph obviously doesn't show you the whole function. So for this one, this looks like an odd polynomial where we're going down and up forever as we move to the left and the right. If it's an odd polynomial, the domain is going to be all real numbers, just like every polynomial. And since it's odd and goes opposite directions as you do the end behavior, that means our range is going to be all reals as well. So all reals for both, that's m, so that goes for spot 17 there. For 18, this looks like the square root function. If that's the case, then our domain is still going to be greater than or equal to 0 for x, and the range will also be greater than or equal to, but this time for y. 0, 0 greater than or equal to, that's a, so that's box 18, which is right there. Number 19 is kind of a bizarre looking graph. I'm not really sure which function family this is, but one side of this kind of looks like the logarithmic function. So I'm thinking maybe, possibly, this is like an absolute value of a log. If you had absolute value of log, then plugging in all these negative x values would essentially duplicate this behavior on the left side. So that's what I'm going with. If that's the case, then the only thing that we can't actually plug into it is 0 for x. That's still going to break stuff. So x cannot be 0. And it looks like there's a vertical asymptote on the graph there anyway. Now for the range, log is, even just one branch of log would give us all the y values. So our range is definitely all reals here. So we've got not equal to 0 and all reals. Where's that? Let's see here. Looking around, there it is, D. We haven't used this one yet, I don't think. So that's going in spot 19. We have a 19 right there, and also another 19 here. So we got double duty for this one. For number 20, this looks to be kind of like a parabola almost with a loop in here. It's an even polynomial if I had to guess. That means the domain is going to be all reals, just like all polynomials. And the range is going to be limited like a parabola. Here we see that we can't go any lower than 0, so y greater than or equal to 0 for that. So all reals and y greater than or equal to 0, that is right here with O, so 20 is O. For 21, this looks like a rational function, maybe a negative version of the original, not really sure. But definitely we can tell we've got an asymptote on both axes, so x then cannot equal 0, and y also, it looks like, cannot achieve a value of 0. So we have two of these not equal zeros going on, and that is going to be right here with I, so that's going in 21. This next function appears to be sinusoidal, either sine or cosine. You can't really tell for sure based off the graph with those, although it looks like this is kind of a cosine-y one. It more easily fits in the cosine framework. In terms of the domain then, we've got all reals, all the x values. For the range, we're bouncing back and forth between positive 2 and negative 2. So negative to positive 2, just like the other sinusoidal function we saw. So that is all going to be another y. We actually get to use y again. That's rare. So that's going in spot 22. For 23, not really sure, but this appears to be some variety of a rational function. This is actually kind of what rational functions look like if you have a 1 over x squared sort of situation. So maybe that's what this is. But just looking at the graph, we can tell there's an asymptote on the y-axis. So x cannot equal 0 because of that. And for the output values, it looks like we can't get any negative values, and it looks like there's an asymptote on the y-axis as well. So we can only get positive numbers out of this one. So that means y greater than 0 is the other piece of this. And that is going to be u right there. That's got everything we need. So spot 23. And we have one letter left to find. So at long last, we come to the last question. There were a bunch of these. This one, you might not know it, but this looks like the function square root of 4 minus x squared. It's a semicircle kind of setup. So for the domain, we can see on the graph here that we can have all the x values between negative and positive 2, but nothing outside of that. So there's your domain. And for the range, we've got 0 at the low end and 2 at the upper end. So 0 to 2 for the y values. And we've actually already seen this set up before. This was another R, so R goes in spot 24. Now that I've filled in all my blanks, I'm ready to solve the puzzle. The riddle again was, what did the king of the real valued functions say to the imaginary numbers? You are banished from my domain. Because he's a king, so he can banish people. And the domain, well, the domain of real numbers does not include the imaginary numbers, right? So there you go. Till next time, Mr. Sutton signing off. I think I got banished as well.